Hi, I'm Ms. Hearn. Let's get started. In counting problems, we're going to look for certain keywords to tell us what operations to use. When we're counting this and that, it's multiplication. This not that is subtraction, and this or that is addition. For example, if 2 cards are drawn from a 52-card deck without replacement, in how many different ways is it possible to obtain a red card on the first draw and a red card on the second? For this problem, we're going to use what's known as the fundamental counting principle. The fundamental counting principle tells us that if you can break a task down into parts, then the number of ways to do the task is the product of the number of ways to do each part of the task. In this case, we have a 2-part task. We're going to draw the first card for the first part of the task, and then the second card for the second part of the task. Since there are 26 red cards in a deck, there are 26 possible red cards to draw first. And if we draw one of those red cards and don't replace it in the deck, then on the second draw, there are 25 red cards left. So the total number of ways to complete our task can be thought of as 26 times 25 equals 650 ways. Anytime you use the fundamental counting principle, you're counting the number of ways to complete the first part and the second and the third and so on. And the use of the word "and" indicates that we're using multiplication. Now let's consider a different situation. The number of ways a certain condition can be satisfied is the total number of possible results minus the number of ways that the condition would not be satisfied. This is called the complements principle of counting. The complements principle of counting uses subtraction. For example, if 4 fair coins are tossed, in how many ways can at least one tail be obtained? Since we're flipping 4 coins, at least one tail could mean 1 tail, 2 tails, 3 tails, or 4 tails, which is a lot of different cases to consider. What we're going to do instead, which is easier, is count the total number of ways to flip 4 coins and then subtract the ones we don't want. So when we ask how many ways are there to flip 4 coins, this is a 4-part task, and we can use the fundamental counting principle. We would multiply the number of ways to flip the first coin, and then the second, and then the third, and then the fourth. There are 2 ways to flip each coin, heads or tails. So we get 2 times 2 times 2 times 2, or 16 different ways, different results that are possible. These results are pictured here in the tree diagram. Each branch of the diagram represents a different result. Notice there is only one branch of the diagram that includes no tails whatsoever. That's the only one that we don't want. We want at least one tail, which is the opposite of none. Only this branch fails to satisfy the condition at least one tail. So from the complement principle, we can take the total number of outcomes, 16, minus the one we don't want, and we get 15 that have at least one tail. Here's another example. If you roll 2 fair dice, we'll assume that one's black and one's white, just so that we can distinguish between the two. In how many ways can you obtain a different number on each die? One way to go about this is to overcount, to count the total number of ways to roll 2 dice, and then subtract off the ones we don't want where the dice are identical, in other words, the doubles. By the fundamental counting principle, the total number of ways to roll 2 dice is the number of outcomes on the first die, which would be 6, assuming it's a 6-sided die, times the total number of possible outcomes on the second die, which is also 6. 6 times 6 is 36 possible outcomes. They're listed here in this product table. What we don't want is for the dice to be identical. So how many doubles would there be? Well, there are 6 doubles. You can think of it as the doubles 1, double 2s, double 3, double 4, double 5, double 6. You could use the fundamental counting principle and say, well, If we roll the first die, we have 6 possible outcomes, but then on the second die, it has to be the same as the first, so there's only one possible outcome there, so 6 times 1 is 6. Either way, we decide that we have 6 outcomes that we don't want. So we take 36 minus 6 and we get 30. This is an indirect approach to this problem. Note that we could have done something else. We could have used a direct method. We could have said, well, the first part of the task is rolling the first die and there's 6 possible outcomes. But then once we know what that outcome is, in order to avoid an identical outcome, we only have 5 possibilities for the second. And we would have had 6 times 5 is 30. So we could use the complements principle, or we could use a direct approach. And either way, we're going to get the same result. Now let's talk about the OR situation, the cardinal number formula. The cardinal number formula basically tells us that the total of this or that is the number of this plus the number of that minus any overlap we may have overcounted. To understand this, consider the cardinalities of sets A and B. Cardinality just means the number of elements in the set. Set A has 10 elements in it. Set B has 6 elements in it. And the overlap, the elements that are in both set A and set B, has 4. So if I asked you for the total that is in either A or B, it might be tempting to add 10 plus 6 and get 16, but that would be overcounting. That would be counting the total number of elements in the overlap twice, which is 4. So to fix that, what we do is we just subtract off the 1 extra copy of the overlap, the 4. So 10 plus 6 minus 4 is 12. In general, the additive counting principle tells us that the number of elements in A union B is the number in A plus the number in B minus the number in the intersection of the two, the overlap. But it's possible that the two sets are disjoint, have nothing in common, in which case the number in A union B can be found by adding the number in A plus the number in B. So you can think of problems asking for this or that, in other words, the union, as addition problems, with one little catch, and that is, if there's an overlap, you have to subtract off the extra copy. We're going to look at 2 examples involving playing cards. Suppose a single card is drawn from a standard 52-card deck. First, we're going to count in how many ways could it be a red card or an ace, and then in how many ways could it be a club or a red. Starting with how many ways could it be a red card or an ace, let's look at a deck of cards, because not everyone is familiar with a deck of cards. And we're going to think about how many red cards there are and how many aces. So here's a picture of a standard 52-card deck. We have 4 aces. We have the ace of spades in the upper left, the ace of diamonds, the ace of hearts, and then the ace of clubs in the upper right. All of the hearts and diamonds are red, so there are 26 red cards. So we have 4 aces and 26 red cards. Is there any overlap between the category of aces and red cards? Yes, the ace of diamonds and the ace of hearts are both red. Keep that in mind. So when we ask in how many ways could it be a red card or an ace, what you should be thinking is, well, since it's an or situation, we want to add together the number of red cards and the number of aces, but we have to be careful when you use the additive counting principle to subtract off any overlap. So we're going to have red cards plus aces minus the red aces, or 26 plus 4 minus 2, which is 28. We could have also answered the question directly instead of using the complements principle by simply counting all the red cards and then the 2 aces that are not red. We would have 13 diamonds, 13 reds, then the ace of spades and the ace of clubs. So altogether we would have 13 plus 13 plus 2 is 28 that way as well. Now let's look at part B. In how many ways could this single card drawn from the standard 52 card deck be a club or a red card? So we want to think about clubs and red cards. Is there any overlap between the set of clubs, which is on the far right, and all the red cards, which are in the two middle pieces? The answer is no, because clubs are black and the diamonds and hearts are red, so they don't have anything in common. When we say use the additive counting principle because it's an OR problem and there's no overlap, all we have to do is add. Clubs, we have 13. Red cards, we have 26. And there's an error there. That guy should be 39 for a total of 39. Another example. A diplomatic delegation of 20 congressional members are categorized as to political party and gender. If one of the members is chosen randomly to be spokesperson for the group, in how many ways could that person be either, and actually I want to change this problem, a Republican or a man? So the number of ways to be a Republican or a man is the same thing as asking for the number in the union of R and M. R union M. So here in our diagram, this 8 in the upper left represents the number of men that are Republicans. The 4 in the upper middle is the number of women that are Republicans. And the 12 on the upper right, well, that's the total number of Republicans. The number 3 is the number of Democratic men. The number 5 is the number of Democratic women. And 8 is the total on in the middle row on the right. That 8 is the total number of Democrats. Along the bottom, we have the total number of men, which is 11, the total number of women, which is 9, and then the total number of people that were under consideration, 20. So if we're trying to find the number that are either Republican or men, then we know that since it's an OR, that it's going to be the additive counting principle. So we're going to count the number that are Republicans plus the number that are men, but we have to subtract off any overlap. Well, the number that are Republicans is 12. The total number that are men is 11. And the total number that are both Republican and men is 8. So we have 12 plus 11 minus 8, which is equal to 15, who are either Republican or male or both. Here's an OR problem where we're going to talk about hands of cards. And we've discussed previously that hands of cards involve combinations. So keep that in mind. So we see the OR. It says how many 5-card hands consist of either all hearts or all black cards. And we know that OR means add. We think about, is there any overlap? Well, the sets of all hearts and all black cards are disjoint. They have nothing in common. In other words, none of the cards that are hearts are black cards. So when we count the number that are either all hearts or all black cards, we're just going to add, and we don't have to worry about subtracting off the overlap. So we're going to count the number that are hearts and the number that are cards. So we're going to count the number of ways to choose 5 cards that are all hearts, and add to that the number of ways to choose 5 cards that are all black cards. You use combinations to do this because when you draw a hand of cards, the order in which you hold the cards does not matter. And there's no repetition since all cards are unique. We're selecting, in the case of 5 cards that are all hearts, we're selecting from a group of 13 cards that are all hearts, 5 of them. So that's 13C5. In the case of a hand that's all black cards, out of the 26 black cards in the deck, we're selecting 5. So we add those two values together. 1,287 plus 65,780. In the previous video, I show how to find those using your calculator or using a formula. The total then is 67,067 different possible 5-card hands that are either all hearts or all black cards. Here's another problem that involves or, even though the word or is not written. It says for the set S equal to CALUTOR, the letters in the word calculator, find the number of subsets with less than 4 elements. Again, finding subsets of a certain size is a context in which we always use combinations because the order doesn't matter in a subset and because repetition is not allowed. So combinations can always be used to count subsets of a certain size. We want subsets with less than 4 elements. So another way of saying that is we want subsets of size 0 or 1 or 2 or 3. By the additive counting principle, then, we're going to add the number of size 0 plus the number of size 1 plus the number of size 2 plus the number of size 3. And notice there's no overlap between those. Those are disjoint. The way that you count the number of subsets of size 0 from a 7-element set is 7C0. The number of size 1 is 7C1, the number of size 2 is 7C2, and the number of size 3 is 7C3. Or 1 plus 7 plus 21 plus 35, which is a total of 64 different possible subsets. Another example of an OR problem would be how many 3-digit counting numbers are either multiples of 2 or multiples of 5. Since it's an OR problem, we're going to use the additive counting principle, and we're going to add the number of multiples of 2 plus the number of multiples of 5 minus any numbers that might be multiples of both 2 and 5. So let's think about what do 3-digit numbers that are multiples of 2 look like. Well, they end in 0, 2, 4, 6, or 8 if they're even. So by the fundamental counting principle, we can count the number of 3-digit numbers that are multiples of 2 by counting the number of ways to select each of the digits. In our system of numbers, the first digit in any number is never 0. So it's either 1 through 9. So there are 9 ways to select the first digit. In a 3-digit number, there are 10 possibilities for the second digit, 0 through 9. But if we know that this particular 3-digit number happens to be even or a multiple of 2, there are only 5 possibilities for the third digit, 0, 2, 4, 6, or 8. Multiplying 9 times 10 times 5, we get 450 3-digit multiples of 2. How many multiples of 5? Well, multiples of 5 end in a 0 or a 5. Once again, the first digit can happen in 9 different ways, and there are 10 options for the second digit, but that third digit has to be a 0 or a 5. So there are 180 different 3-digit multiples of 5. And how would we distinguish those numbers that are both multiples of 2 and multiples of 5? Well, which one do they have in common? Which number endings do they have in common? They must end in a 0 if they're both a multiple of 2 and a multiple of 5. So we would take 9 possibilities for the first digit, 1 through 9, 10 possibilities for the second digit, 0 through 9, and then only 1 possibility for the third. 9 times 10 times 1 is 90. So by the additive counting principle, we would add 450 plus 180 minus 90 and find that there are 540 3-digit counting numbers that are multiples of 2 or 5. So we saw that when we have a counting problem involving and, we use multiplication because we use the fundamental counting principle. When we have a problem involving not, then we use subtraction, and that's the complements principle. When we have a problem involving or, we use addition, which is the additive principle. I hope you found this video helpful. If you did, please remember to give it a thumbs up. That helps other students to find the